Okay, so in 3.4, we start talking about a new term, concavity. We also have these things called points of inflection. All right, but first, when we talk about concavity, what I'm saying is if we have a differentiable function, then we can either be, that function can either be concave up or concave down. You might have remembered concave versus convex in geometry. In calculus, we're just going to say concave up. And when we say concave up, like a cup, okay, so it could look like this, it can look like this, like this. There's other ways it can look. And concave down, like a frown. So concave down would be a parabola like this, or maybe a graph like that. And so you can kind of see intuitively, maybe you can tell the difference between the two. All right, but what we're going to focus on is this whole idea of the derivative. Okay, the derivative is increasing when we have concave up, and the derivative is decreasing when we have concave down. You can almost think of concavity like acceleration, okay? Whereas if the function is just how far you've gone in your car, the derivative then would be your velocity, okay? And concavity has to do with the second derivative, or the acceleration, the rate of change of the rate of change. All right, so if f prime is increasing, then we know that f double prime is positive, okay? On the other hand, if f prime is decreasing, then f double prime is negative. This is just like how it was before when we just were comparing f to f prime. Now we're comparing f prime to f double prime. And so when f is concave up, let's think about how this relates to the tangent line. So here we have a graph. I've just made it a simple parabola. Then we have the tangent line. This graph is always going to be above the tangent line. Okay, on the other hand, we have a parabola down, and we have a tangent line like this. We can see that the graph of f lies below its tangent line. So I want you to notice that on one hand, we have a lot of positive language. We have f prime increasing, f double prime positive, concave up, f lies above the tangent lines. Those are all positive words. And when we have f prime decreasing, f double prime negative, concave down, graph of f lies below. So that's a way you can kind of group them together. All right, now looking at this graph, I'm not given the equation. All right, so we're just going to look at the picture first. I can see that the first part of this graph is definitely concave up. All right, it's definitely concave up, like a cup. Now this section from somewhere around -1 looks like it's concave down, and it's kind of hard to tell, but I'm going to put a point there, and I'm going to put a point at 0, 0 as well. This little section right here, the graph is actually concave down. Okay, it's subtle, but it is. Okay, right after x equals 0, the graph becomes concave up again, and right about 2 is where it changes. So this part of the graph is concave up, and then the last part of the graph is concave down. All right, these points right here, we're going to call points of inflection. I'm going to define that kind of at the bottom of this page, but we're going to call those points of inflection. That's where the concavity changes. All right, so I want you to know when the graph is concave up, okay, in this section right here, this means that f prime is increasing. It also means that f double prime is positive. Okay, and then there's a similar thing that, this same thing happens for the other part of the graph that's concave up, and then the opposite's happening when the graph is concave down. So then we get to this theorem, this test for concavity. If f double prime is greater than 0, in other words, if f double prime is positive, then the graph is concave up. You already saw that. This is just a theorem stating it. If f double prime is negative, then the graph is concave down. Okay? This is how we're going to determine concavity when we're given an equation instead of a graph. Okay? We're going to find the second derivative. We're going to test where we have an interval where the second derivative is positive, negative. That's going to tell us concavity. Well, when the graph is between concave up or concave down, or when f double prime is between positive and negative, in other words 0 or undefined, these x values are going to separate our intervals, okay? This is kind of like critical numbers, all right? But critical numbers were with f prime. This is for f double prime, all right? And again, this is going to be points of inflection, so I want you to just go ahead and draw an arrow there. All right, let's go ahead and determine the open intervals of which the graph of f of x is concave up or concave down. Okay, so let me scroll up just a little bit. So we can say that f is concave up on the interval. Okay, it looks like negative infinity to negative 2, and then it picks back up from 0 to 2. Okay, likewise, f is concave down, and this is happening on the interval negative 2 to 0, this part right here, and union that up with 2 to infinity. Now, if we were to put a reason at the end of this, if we were to put a because, what we're going to be, we could say really two different things. We could say because f prime is increasing, but more likely we're going to relate this to the f double prime. So remember, concave up was when f double prime was positive, concave down was when f double prime was negative. Okay? We're just getting used to writing this out more and more each day. Okay, points of inflection. When the tangent line exists at a point where the graph changes concavity, that point is called a point of inflection. Okay? The concavity of a graph changes at a point of inflection. All right, so we've seen kind of what this looks like in the graph above. Let's go ahead and write down our points. Now, our points of inflection, we know the x values, okay? We do also know the y values. But when we're generally given an equation, at first, all we're going to know is the x values. Now, in this graph, we can just look up at the top. It actually worked out kind of nice. But in the future, we're going to have to go and we're going to have to plug into f of x, the original equation, to get y's. Okay, sometimes I'll just ask you for the x values. Most of the time, if I'll say the point of inflection, you need to list the x and y. Okay, so here we have this c and f of c. This is just an x and a y value. That is a point of inflection, or if that is a point of inflection, then we know one of two things is happening. Both of them have to do with f double prime. F double prime is equal to 0, or f double prime is undefined. Again, this is like critical numbers, okay? But critical numbers were with f prime. Points of inflection have to do with f double prime, okay? So let's do an example now where we're not given the graph. It says, determine the points of inflection and discuss the concavity of this graph. Okay, we need to start with the derivative, the first derivative. So that's going to give us 4x cubed minus 12x squared. All right, this, if I wanted to go and do all that stuff we did before, relative mins, relative maxes, increasing, decreasing, I would go ahead and set this equal to 0. I would find my critical numbers and all of that, okay? But because this is only asking me about points of inflection and concavity, this is all second derivative stuff. So I need to go ahead and find the second derivative. So I do take the derivative of the derivative. All right, and so now is where I get to do all the fun stuff that I did before, okay? So I check to see, okay, is the second derivative, f double prime, is this ever undefined? Well, no, it's just a parabola. So I get to set this equal to 0, and I solve. Same way to how I solved before. On a lot of these, you're going to just get to factor pretty easily. Okay, so I have two numbers, x equals 0 and x equals 2. These are my points of inflection. This is where the graph changes concavity. Well, it's actually half of my point of inflection. I am going to go ahead and write it as coordinates. And in order to find the y, you have to go back to the original. Okay, anytime you're given an x and you need the y, you have to go back to the original. So we plug in, and I'm not going to spend a lot of time on this, but we get negative 16. Okay, so these are your points of inflection. If I only asked you where are your points of inflection or what's the x value, you know, we would only list that. But generally, I'm going to want you to write the whole point. Okay, so that checks off that. Okay, now let's talk about concavity. Okay, let's make a sign chart. Again, SIGN, meaning plus and minus. And this time, I'm going to compare my function to the double derivative. Okay, so let's take a number that's less than 0, a negative number, and let's plug it in to the double derivative. And you can plug it in here, or you can plug it into the factored form, whichever one is easier. If I plug in a negative number into my second derivative, I'm going to get a positive number. This, you know, before, when down here we were talking about f prime being positive, that told us that f was increasing. When we have f double prime, it's going to tell me about concavity. All right, so plus means concave up, and I'm going to go ahead and draw a little picture. Now, it may not look exactly like this parabola, but it gives me a good idea of where I'm going. Okay, now I'm going to plug in a number like 1. Okay, that's going to give me a negative when I plug it in. And again, I'm not spending a lot of time on this arithmetic. So please ask questions if you have them. Okay, plug in a number larger than 2, f double prime, second derivative, plus, that's another concave up. It looks like this. Okay, so this doesn't really tell me about mins and maxes. It tells me that I probably do have a max somewhere between 0 and 2, not necessarily the middle, but somewhere in there. Okay, I could probably deduce that. I don't know for sure about the outsides. I mean, there's still more to be determined, but they don't ask me about it on this one. They're just asking me about concavity. So let's think about this. F is concave up on, and we just follow the sign chart. Negative infinity to 0, and then again from 2 to infinity, and we do need to write a because here. We're going to do a justify because of this little word discuss. That kind of implies justification. F is concave up on this interval because f double prime is positive. Okay, likewise, f is concave down on 0, 2 because f double prime is negative. There you go. We've discussed it. Okay, one more thing in this lesson is that has to do with this thing called the second derivative test. What the second derivative excuse me. What the second derivative test measures is it's another way to find maxes and mins, but using the second derivative. Okay, so this says f is a function such that f prime of c equals 0. This means the derivative is equal to 0. They're basically saying c is a critical number. Okay, so max or min, horizontal tangent, something like that's going on. Okay, if the second derivative exists, meaning that we are able to take the second derivative, then I can actually do, instead of doing the sign chart for f prime, I can go and I can do f double prime and not even do a chart, but just like plug it in. If f double prime at that critical number is greater than 0, this means I have concave up. Look what happens with concave up. Right down here I have a horizontal tangent, and that's a min. Okay, on the other hand, f double prime less than 0, that's concave down. Again, I have a horizontal tangent, that's a max. Now, if double prime of c is 0, this is getting into points of inflection and the test fails, and so we'd have to do something else. I will tell you there is kind of a weird scenario where you have a critical number because the first derivative, like here, this is f, the first derivative is 0, the slope right here at this point is 0, so that's a critical number, but it also, it's a point of inflection because half the graph is concave down, the other half is concave up, so this generally happens when x is 0, but not always. All right, let's go ahead and use the second derivative. So again, first things first, we need to find the first derivative. Always start there. So we have negative 15 x to the fourth plus 15x squared. And in this case, I do need to find the critical number. So I'm going to go ahead and set this derivative equal to 0. I'm going to factor out negative 15x squared. I'm left with x squared minus 1, which I can factor further into x minus 1, x plus 1. So then my three numbers, x equals 0, x equals 1, x equals negative 1. These are critical numbers, okay? These are the numbers where I have horizontal tangents. It's possible maxes and mins, all right? Before today, if I wanted to know which ones were maxes and mins, I would do the sign chart and talk about increasing, decreasing, and all that, okay? And we could do that, okay? Sometimes, though, in fact, a lot of times it's going to be easier to do this thing called the second derivative test. Okay, second derivative is going to be negative 60 x cubed plus 30x. And the reason second derivative test may be easier is because, look, every time you take the derivative, you go down an exponent. And so the number crunching is actually a little bit easier, usually. So here's my second derivative. I need to know at these 3 points, is the second derivative positive or negative? Now, we could arrange this a variety of ways. I'm going to go ahead and do a t-chart here. I'm not doing intervals, okay? That's why I'm not doing a sign chart. I don't want to know between 0 and 1 what f double prime is. I want to know when x is 0, okay, what is f double prime? Well, that is 0 as well. That doesn't really tell me anything. This was the third case right here. All right, so we don't have a max or min. In fact, we're going to have a point of inflection there where the graph changes concavity. Then we plug 1 in for x, okay? Again, I'm not going to do a whole lot with the number crunching, but you're going to get a negative value. You get negative 30, in fact, but I don't really care so much about that. I just get a negative. Now, when f double prime is negative, that means my graph is concave down. Because this is with a critical number, I now know that that's where I have a max, a relative max. Okay, last we would do a negative 1, and when I plug in negative 1, I actually get a positive result. Positive f double prime means concave up. With a critical number, that means I have a min. All right, so this was maybe easier, probably about the same level. I want to go ahead and go over here and show you kind of the other way that we did this. Okay, what we did before was we took values, we plugged them into f prime, then we had f up here, and we saw that on the left side, if we plugged in a large negative number into the derivative, we had a negative, therefore my graph was decreasing, okay? And then we started to have to plug in like fractions, okay? This graph is going to go up because we have a positive here. I think we have a positive right here, negative here, so the graph ends up looking something like this. And from this, in this, again, we've done the work. We're done with this problem, but what I'm doing over here is just reinforcing it. I know that I have a max going on at positive 1 and a min going on at negative 1. But in order to get this, I had to use fractions. I had to plug fractions in, figure stuff out, and that can get messy, and on other problems it gets even more messy. Okay, so the last thing I need to do is write my answer, okay? We'll fill in these blanks in a minute, but I'm going to use this down here. So we would say that f has a relative max of, oops, I don't know what the max is yet. I wouldn't have known it whichever way I did it, so we'll come back to that. At x equals 1, and the reason is because f double prime of 1, remember, was negative. Okay? Likewise, f has a relative min of, again, I'm going to have to go back to figure that exact value at x equals -1 because f double prime of -1 is greater than 0. Okay, you don't have to memorize this right here. Just think about the concavity. Draw a little picture if you need to. That'll tell you whether you're dealing with a max or a min. So always when we need to know the y value, we got to go up to the original problem. So it looks like when we plug in regular +1, we get -3 plus 5 is 2. When we plug in -1, we get -2. I'm just going to double check that before I finish. Yep, plug in -1, we get -3, it's +3, minus 5, -2. Okay, sorry, just wanted to double check that since I'm not doing this video in front of a class. Alright, now to fill this in, last thing. If the graph of f is concave up, and we have a critical number, that's what that means. So we have concave up, and we have a critical number. Critical number means basically horizontal tangent line. Then that point has to be a relative min. Okay, you don't have to memorize this. In the other way, we're going to get a max. That's because we have concave down, horizontal tangent. If you just draw a little picture and think about concavity, it's really easy to figure out. Okay, don't memorize what you don't have to.